Tamamdır hocam, ben başlatayım.
Problem setini gönderdin herhalde.
Evet. Hi everyone. This is the fourth lecture of Calculus lecture series, and today and also following lectures mainly we focus on problems and some exercise. Then we can start hocam.
Okay. So I have prepared some problems for you to get used to what we have learned up to now, but they are difficult problems. Allow Zoom to share your screen. Ne oluyor?
You can share hocam.
Referanslar, vay Allah. Ya okay. Zoom will not be able to record the contents of your screen until it is quit and reopen. Okay. Dün biraz oynamıştım da bilgisayarla. Bazen sayfalar büyüyüveriyor. Bir bug var, onu bulma uğraştık, beceremedik. Okay. So today we shall make some problems, essentially, and I have chosen some difficult problems. They are not very easy, so but they are also interesting for you to learn new concepts. Okay, so for instance, we shall begin first with some problems about the Sigma Algebras. Okay, so the first problem, as I have sent you, it says that it defines a set of sets. Okay, so the problem first says that let omega be any set, and X is the subsets set of subsets of omega, such that either the set or its complement is countable. Of course, countable comprises the word finite also. Okay. Now, the question is, first show that X is a Sigma algebra. X is a Sigma algebra. So to do this, well, we know that there are three conditions for a family to be a Sigma algebra. Is the total set omega is an element of X or not? Well, if you take the complement of omega, it is empty set, it is countable, it has 0 elements. Hence, this implies that omega belongs to X. So the second property is that if A is in X, do we have A complement is in X? Well, if A is in X, it means that its complement is countable. Hence, or A is countable. If A is countable, then it is a complement has a countable complement. Hence, complement is also in X. Okay, so this implies if A is in X, so there is one proper possibility if A is countable. This implies that A complement, which is equal to A, is countable. Hence, this implies that A complement belongs to A also. Otherwise, if A complement is countable, then it, again, same story, A complement has a then A complement complement of A is countable. This implies that A is in A is in X. Okay, so this is all triviality. The third property is that if AN is a sequence from X, is their union from n to infinity, AN is again in X or not. So required to prove it means that 1 to infinity AN, let me call this B, is B or B complement countable. Okay, if B is not countable, B is not countable, then this implies that there exists at least one AN which is not countable. So this implies then that it is complement is countable. So this implies what? Let me see. So if I haven't, if B, well, let me maybe take the intersections, since I can show that if the intersection is again in X, it is the same thing. Intersection is easier because let B be the intersection of ANs from 1 to infinity. I have to show that either B or B complement is countable. Okay, so if B is not countable, this implies that no AN is countable. So this implies that all the AN complements are countable. Hence, their intersection, their union is countable. Countable union of sets is countable. Hence, this implies that union of AN complement is in X, hence union of ANs is in X. Okay, so it is easier to show with intersections. So this is either then we have supposed that this thing is not countable. If B is countable, contrary, so if B is countable, then well, there is nothing to prove because this is a definition of being an element of X. This implies that B is in X. Hence, X is also stable under countable intersection, hence also countable union by complementation. Okay, so when you are stuck with one thing, try to think about the other. Okay. Now, the second question is about the structure of the Sigma algebras. If I take a Sigma algebra on a non-finite set, then claim says that this cannot be countable. Countable means you can count the elements. For instance, natural integers is a countable set, but real numbers is not countable. Okay, so the definition of countability, if you can put them into one-to-one correspondence with integers, then we say that it's countable. Okay, did you see it somewhere, Rüştü, or it is new for you as concept?
We know the countable and uncountable. We know actually countable and uncountable concepts from discrete mathematics.
Yeah. So, okay, the challenge is, so if omega is not a finite set, if is at least countable but infinite countable, if omega is at least countable, then sigma, there is no sigma algebra, no countable sigma algebra. Well, the question is not well posed, containing, okay, where whose, okay, such that the points of x omega are okay, so the one for any x of omega, this is an element of the sigma algebra. Question, let me verify the question. This is not very well posed.
You said prove that there is a no countable
Sorry?
sigma. You said prove that there is no countable sigma.
I will prove it. I will prove it. I will prove that this cannot be countable.
Okay.
This is a difficult question. Okay, I will suppose that the contrary is satisfied. So let F be a countable sigma algebra on omega. So I don't suppose this hypothesis. Sorry, this is not correct. So let, for x in omega, I will denote by f sub x is all the elements of the sigma algebra which contain x. Then I take ax to be intersection of these people. As sigma algebra f is countable by hypothesis, this fx is countable, hence this is a countable intersection, hence this thing is an element of the sigma algebra, f again. Okay? Now, the thing is that if B is any measurable set, any element in F, then either B is greater than Ax or B and intersection Ax is empty. This is the claim, first claim. Why this is true? Well, suppose the contrary. Suppose that Ax intersection B is non-empty. Of course, this doesn't imply that X belongs to B. But suppose that they are non-empty. Hence, in this case, X belongs either Ax intersection B or Ax intersection B complement. Because union of two is equal to Ax. Okay, so if if X belongs to the first one, well, this is a contradiction because it means that since Ax, the smallest measurable set containing P, this implies that B should be equal to AX. By definition of AX. Okay, this is the definition of AX. If X belongs to AX intersection B complement, well, since AX is the smallest subset containing X, this implies that AX is subset of B complement. Hence, this means that AX intersection B is empty. Okay, so this settles the problem. It means that you take any set, measurable set B, then it is either a superset of AX or they have disjoint intersection. Okay, so it is, this thing is a little bit tricky. You have to be careful. Hence, if we take from this, if we take any two elements of omega, then either AX intersection AY is empty or AX is equal to AY. Because AX cannot be a subset of AY, because in this case, okay, AX cannot be super. Okay, let's see what happens if then if they are not empty. Okay, if AX intersection AY is non-empty, then we come to the first situation. So this implies that AX will be a subset of AY, and AY will be subset of AX, hence this implies that AY is equal to AX from above. Okay, so this settles in such a way that we can associate to each element of omega a set coming from the sigma algebra. And since these sets are countable, because F sigma algebra is countable, we can write the family AX when X runs in X as we can write it as indexed with a subset of integers AK. K is in I, and I is a subset of natural integers N. Okay? Now, from what we have seen, as AX and AY are have empty intersection for different X and Y, this is translated by saying that AK intersection AI is empty for any I different than K. Okay, so if I take any subset of I, let's say D, will be again countable, then and I write A sub D as the union of AIs for those I in D, then this is again a measurable set, because there is a countable union of measurable sets is measurable. So if now I take two sets D and E subset of I, then such that D is different than E, then this implies that AD is different than AE. It cannot be equal because in this case there will be some AI will be equal to AJ, etc. This gives you a contradiction from what we have done. So otherwise, if not, you would have AI intersection AJ non-empty for I different than J. Okay, hence this implies that AD equal to AE implies that D is equal to E. The just negation of the first thing. Okay. Hence, this implies that the map which sends the subsets of I to A sub D, this is a bijection. Bijection. There is no E here. Okay. But what is this? The family of these, D is the set of sets which are subsets of I. Cardinal of this is equal to 2 to the I. And this is an uncountable set. Is uncountable. The number of subsets of a set of n elements is 2 to the n. Okay. So this, if this n is countable, 2 to the n is uncountable. This is the first non-uncountable cardinal. I don't know if you have learned these things. So this gives you a clear contradiction to the, because from ADs, the set of ADs is countable from what we have seen above. Though the set AD, the subset of I is countable. Hence, this is a contradiction. Okay, so this is a nice result. Okay. There is a third question. These questions, I have chosen them as necessary things for you to learn to facilitate lectures which are to follow. Okay, so that's why they are a little bit hard, but you have to work them at home. You cannot follow directly like that. Okay, this is the level is high. So the third question I have sent you, it concerns, for instance, we take a topological space X. Let's say take real line if you want, okay? And then we have defined the Borel sigma algebra on it. This is the smallest sigma algebra containing open subsets of X. Sigma algebra containing open subsets of X. So we say that it is sigma algebra generated by the open subsets, or equivalently by closed subsets, which are by complementation. Okay. Now suppose now that instead of X, I am dealing with a subset of X. Okay. Let then Y be any subset of X. Now we speak about the induced topology on Y, topology inherited from the X, any open subset on this topology. So if, sorry, I don't know what's happening. So we take the open subsets of X. So we take O, which belongs to open of X, and we say that a set is open in Y if it is intersection of O with Y. Is open in Y. This is the subspace topology, this topology. This is called subspace topology. This is the general definition. So you say that, for instance, in subspace topology, a sequence yn converges to y if the distance between yn and y for large n will be in a neighborhood of the type O intersection y. Okay, or yeah, this is the most general definition. You can apply it, for instance, when you take an interval like that, half closed, then the topology, subspace topology of this is the intersection of this with the open intervals of the whole line. Okay, so this is the definition. Hence, we want to know what happens to the Borel sigma algebra of Y. So the claim is that the sigma algebra on Y, which is generated by the open subsets of Y, can be written as, so B of Y is equal to just Y intersection A. A is a Borel subset of X. So this is claim here, is hidden here, is that smallest sigma algebra on Y containing O intersection Y, O open in X. This is what it says, the claim. Okay. I think I will leave this for the while, but put it somewhere in your memory, because I am afraid that you are not very well acquainted with topology yet. Okay. We shall come to this later in time. Let me come to more probabilistic things. Is it okay with you?
Okay, hocam.
Okay.
That's fine.
So let's come to some more probabilistic stuff. So this is problem 4. Let us take as probability space omega to be equal to unit interval. And as probability P, I am taking the Lebesgue measure. And as a sigma algebra F, we are taking Borel sigma algebra of 0, 1. So the claim is that if you take a subset of omega, which is measurable, A, so belongs to B of omega, which is F, sorry, and if it is probability is equal to 1, then we claim that A is dense in 0, 1. Then the set A is dense in 0, 1. I don't know if you know what dense means. Do you know it or not?
No,
Rüştü?
I don't know.
So we say that a set is dense in 0, 1 if any element of 0, 1 can be approached as the limit of a sequence chosen from the elements of this set. Okay, this is a very important concept. So for instance, rational numbers are dense in the real numbers.
Okay.
Okay, so equivalent condition for to be dense, so A is dense in a topological space X if and only if any open subset of X has a non-empty intersection with A. This is the general definition of denseness, and if you can measure the distance, then you come to this story of the sequences. They are equivalent. Okay, this you have to learn these things. These things are essential because when we shall do martingale representation theorem, with stochastic integrals, this is one of the goals of Ito calculus, I will need this concept. Okay, so dense concept, this is important. This is an old subject you can find in Wikipedia. Okay, it is abstract, but it is not new. So using this characterization of denseness, A is dense in the unit interval 0, 1, if and only if for any non-empty interval AB in unit interval 0, 1, A intersection this interval AB shouldn't be empty. If I can show this, then I will be done. Okay. Now, let us take any open subset of unit interval then. Let O be any open subset of the interval 0, 1, open. So in particular, O may be an open interval. Okay. So, and suppose that A is not dense. If A is not dense in the interval 0, 1, then there should be such an open set such that O intersection A should be empty. Just the negation of this. Okay, so let's calculate then union of O with A and its probability. This is equal to probability of O plus probability of A minus probability of O intersection A, which is empty, hence it is 0, that's all. Now, this is then, since probability of A is equal to 1, this is less than or equal to 1, and this is equal to lambda U plus 1. Hence, this implies that lambda U is equal to 0, probability of U. Okay, but I know that since U is open by definition, then U should contain an interval of the type A, comma, A plus epsilon. Hence, this implies that measure of U is greater or equal to measure of A, comma, A plus epsilon, which is equal to epsilon, which is strictly positive. Hence, it gives you a contradiction. Hence, this implies that then A is dense in 0, 1. This is a very strong result. It's true also in higher dimensions. Same proof. Okay. So this is an important thing. For instance, when we had studied the notion of the convex functions on the Wiener space, on a probability space, we have needed this property. Okay. Now let's come to more, let's say, closer subjects. It's about the lim sup and lim inf and independence. Okay, this is problem 6. Okay, let us take a standard probability space omega fp. This may be very well the unit interval, if you wish, 0, 1, Borel Sigma Algebra fit and the Lebesgue measure in particular, but we don't need this particularity. This is a general result. So, and let me choose Xn, a countable family, a sequence of random variables, real random variables, in R, with values in R. Okay, now the first thing is that I want to show if lim sup of xn and lim if of xn are measurable again, are again random variables. This is the first question. Okay, so let me recall the property, the definition of lim sup of xn of omega. This is, you are taking supremum of xk of omega for k greater or equal to n. Then you take limit the rank n, you push it to infinity. Okay, so this is a function of omega, and we know that this thing is measurable if and only if is measurable with respect to f, if and only if for any integer, or sorry, for any number t, real number, y less than or equal to t is an element of f, or we are not confined, y less than t is an element of f, or the complements y greater than t is an element of f, or y greater or equal to t is an element of f. You choose the simplest test that you need. Okay, so for instance, let's look the first one. Okay, so limit as n goes to infinity, the supremums decrease. So there's a decreasing sequence of supremum k greater or equal to n xk of omega. So this is if this is, for instance, less than or equal to t, this means that this is equivalent to saying that there exists at least one n such that there exists one n at least such that then supremum k greater or equal to n xk of omega is less than or equal to t. So what does it mean? This means that union with respect to n 1 to infinity, that supremum xk of omega is less than or equal to t. K greater or equal to n. Okay. Sorry. It's not good, well written. This is the same thing as union n 1 to infinity, that there is supremum k greater or equal to n xk of omega is less than or equal to t, at least one n. Okay, and this thing is the same thing as, since the supremum is less than t, anyone should be less than or equal to t. So anyone, I can write like that. Since xk is measurable, this set belongs to F, countable intersection belongs to F, and countable union belongs to F. Hence, this belongs to F, then you are done. Okay, for lim if of xn is equal to lim sup of minus xn with a minus sign here, then you are done. Hence, done also. Okay, the reason for this exercise is that second part, prove that let A with the set of convergence of the sequence xn, limit xn of omega as n goes to infinity exists. I claim that this set is measurable, so it belongs to F. This is the claim. Okay, well, let me call by x bar like that this lim sup of xn, and with x bar bottom lim inf of xn, then A is equal to the set of omega such that x bar upper bar is equal to x lower bar of omega. Okay, hence this is the same thing as omega such that x bar of omega minus x lower bar of omega is equal to 0. Hence this is inverse image of x bar up, x bar minus low minus 1 of the closed subset of real line 0. Since this difference is measurable, this belongs to F by definition of measurability. Because 1 point set 0 is closed, hence it belongs to the Borel Sigma algebra of R. Since the set 0 is closed. Okay, so this shows you that the limit, the set on which the limit xn exists, it may not exist for any omega, but for those omega for which it does exist, it is a measurable set. Hence, I can talk about its probability. And I can take integral of function on it. This is very important. This should be done at least once in your life, this proof. Okay, the third question is, I leave it to you. If x and y are two measurable or real random variables, prove that their sum is measurable. This is important, but it is not immediate. You have to work a little bit. Here you have to work with the fact that you can approximate the reals with the rational numbers, etc. Okay, so this is homework. I will not do it. So this is about the measurability. Now let me come to measurability related to independence. Okay, maybe I will make a break in 2 minutes. Let me recall you first the definition of independence, okay? So this is an important subject. We are in a probability space, omega fp. Then we say that this is the general definition. We say that two finite subsets of random variables x1, xk, and y1, yn, all real value, to clarify the ideas, are set independent if expectation of product from 1 to k of fi of xi, times product from 1 to n of gj of yj, this is equal to product of the expectations. 1 to k fi of xi times expectation of product 1 to n of gj of yj. This for any fi and gj which are continuous and bounded on R. CB means continuous and bounded functions. This is the most general definition of independence of two finite families of random variables. This is the first one. I will not, then I will say that two arbitrary families, so X alpha, alpha is in I, and Y beta, beta in J, are two arbitrary families of real random variables, are set independent if any finite subfamily of the former is independent of any finite subfamily of the latter. So for this, we use the preceding definition. Okay? And in this case, I do this because then we can talk about the independence of the sigma algebras. Okay? So we say that, for instance, let F and G be two sigma algebras on the same probability space on omega, let's say a big sigma algebra A P, where F and G are subsigma algebras of A. Then we say that F is independent of G. This is the shorthand notation for independence notation. If then any indicate I take any subfamily, so and I take their indicator functions. So okay, I associate if A belongs to F, then I associate to it indicator function of A in both way. Okay, so if this IA's A belongs to F are independent of IB's B belonging to G. Okay, this is the definition, so everything is in order here. Okay, so this is the most general definition of independence. We will not need more than this. Okay, so I will use this concept to make some exercise. I'll make a break to drink some water. Rüştü bir tek ikimiz kaldık galiba.
Evet hocam.
Geri gelenler olacak mı sence yoksa?
Hop. Yani hocam inşallah olur.
İyi.
Ha,
Hayır, tek başınaysan takip ederken soru daha rahat sorabilirsin. Yani onu da unutma.
sonda sorabilirim. Şimdi son soru zaten 7. soru son değil mi hocam? Aslında.
He?
Attığınız problem sette 7. soru son soruydu sanıyorum.
Evet. Şimdi bitireceğim zaten ya.
Ha, tamam, sonrasında sorabilirim.
İyi.
Bir şey soracaktım.
Ya bunlar ciddi zor sorular. Bilhassa seçtim ki yani zaten kolay sorular herkes bulur şeyde. Onları İhsan çözer size ayrıca. Eğer hala ders olursa tabii ki.
Yaparız hocam.
He?
Yaparız hocam, ben yani İhsan Hoca.
İşte anladım. Bakalım, bakacağız. Okay, now let's come to this last question. This is a very nice question. It's here that you see the difference between probability and deterministic calculus, the analysis. Okay, so the first thing is that suppose that A is a subset, measurable subset of omega, and assume that it is independent of itself. Okay, so this is 7-1. A is independent of itself, hence it means that the indicator function of A is independent of itself, hence it means that probability of A intersection A, which is equal to expectation of indicator of A intersection A, hence I can write it as expectation of intersection of A times indicator of A times twice. This is equal to expectation of indicator of A square. So this implies that this is equal to probability of A square. Hence, by elementary calculus, probability A is equal to either 0 or 1. Okay, this is the easy question. So this was the clue. Now, suppose the same thing, not for a set A, but for a random variable X. So probability X is less than or equal to T. This is independent of itself, hence this is equal to 0 or 1. From 1 for any T. Now, recall that the function of this thing, this is called probability distribution function, is an increasing function, is increasing. Hence, this implies that there exists a smallest T0 such that this thing is equal to 1. Since it's increasing function, it will be, and you know that it will be 1 or 0. Well, after some t, it should be 1. If x, of course, if x is not equal to already minus infinity, and we exclude this possibility. If x is equal to, if this is 0 for all t, it means that probability that x is any takes any value in R is 0, hence it is equal to x minus infinity. This, we exclude this situation. So let me then this is equal to 1, and probability x less than t0 is equal to 0. Choose, in other words, let t0 be the infimum of the points S such that probability X less than or equal to S is equal to 1. Hence, this implies that probability X less than or equal to T0 minus 1 over N is equal to 0 by definition of minimum, and in infimum probability X, so probability X less than or equal to T0 plus 1 over N, this is equal to 1 by definition of infimum again, and it is increasing. Okay, hence this implies that probability that X belongs to the interval T0 minus 1 over N, comma, T0 plus 1 over N, this probability is equal to 1 for any N positive. Hence, if I take the intersection of these people with respect to N from 1 to infinity, for instance, that X is in the interval, these intervals, T0 minus 1 over N, T0 plus 1 over N, this intersection has probability which is equal to 1, because each of these has probability is equal to 1, and this is a decreasing sequence, okay? So probability of, call this Pn, probability of intersection of Pn's from 1 to infinity, since Pn's are decreasing, this is equal to limit as n goes to infinity, probability of Pn, limit of 1 is equal to 1. This follows from the sigma additivity of probability. This is very important. You cannot teach them to undergraduate students of engineering without defining Kolmogorov axioms. Okay, this is here you see the importance of the sigma additivity of a probability, for instance. And this set is equal exactly probability that X is equal to T0. Hence, it is equal to 1. That's why then we say that X is equal to a constant, is constant P almost surely. Okay, so what is the use of this thing? Now, let's see what happens. This is the third part. This is becoming interesting. Let then Xn be a sequence of real random variables which are independent. Be a sequence of independent real random variables. You can produce this by computer when you simulate a random variable with low Gaussian, for instance. You call there is a command which is called randomize. You call random numbers. This gives you a distribution, uniform distribution on 0, 1. Then you compose it with the inverse function of the probability distribution function of Gaussian. This uniform, it gives you the Gaussian random variable. Then you call again randomize, it erases all the memory, and you recreate again another random variable Gaussian, and in this way you obtain independent copies. This is called simulation. This is a very important thing in technology. Okay, so I mean by that it is very easy to obtain independent copies, independent random variables. So I claim, let me call, let X be the lim sup as n goes to infinity, supremum of Xn. Okay, then if you look at this, this is limit as n goes to infinity, then supremum k greater or equal to n of xk. Okay, so if you take any random variable xn, and you call this sequence, let's say Zn, then Xn is independent of Zn plus 1 for any n. And not only Xn, but X1, X2, all the preceding one up to Xn, this set is independent of this for any n. And this implies that also X1, Xn is independent of Zn plus k for any k. Okay, as this people goes to x, as k goes to infinity, then you find that X1, Xn is independent of the lim sub x. This is for any n. And as x is independent with respect to sigma algebra generated by xk's, then this implies that x is independent of itself. This is deep mathematics. Hence, this implies that x is almost surely a constant. Okay, let me give an example of this. Let us take a sequence. Let S omega t be this series, random series, whose coefficients are random, xn of omega from n1 to infinity times t to the n. Okay, so the radius of convergence of this sequence, it is defined, I don't know if you have learned this in calculus, then it's called rho of omega. This is equal to lim sub of xn to the 1 over n. Then we find this then that rho omega is independent of itself. Hence, it is a constant. Is equal to a constant p almost surely. So this means that the radius of convergence of this series is constant, although the coefficients are random. Okay, hence probability that of omega such that S of omega t converges, this is equal to probability that the t is less than radius of convergence. This is equal to either, I don't know what happened, I have lost. Sorry, everything has closed down. I have refound them. So this is the same thing as, this is the same thing as t less than rho. This is either 0 or 1. So as you see, you obtain very fine results using this concept. This is a famous result of Kolmogorov. This is called 0-1 law. Okay, Rüştü, I will stop here. I think you have enough material to study. And these things are really important because, for instance, when we study the convergence of lim sub of Brownian motion, this kind of stuff, we use these properties. Okay, so these are very important in the applications, although they seem very theoretical. Okay, so thank you for listening to me. I have sent you